So today we will start our next lecture 12, and this essentially begins chapter 3 of my book. And today's lecture we are going to discuss the gradient vector and some of the key properties of the gradient vector which make it very useful in optimization. Now in previous lectures we assumed that the search direction D was known, and we looked at different methods to calculate the step size. And from this lecture forward in chapter 3, we are going to look at different methods for determining the search direction D, such as the steepest descent method, conjugate gradient method, and so on. Now, most of these methods which try to find out the search direction D are classified under so-called direct methods. And the aim of these methods is to find the search direction such that the function f of x decreases rapidly. And the methods we are going to consider in this chapter 3 are essentially those which use the first derivative of the objective function or the gradient vector in case you have a multidimensional function, which is generally the case. Now in the next chapter, that is chapter 4, we are going to look at methods which use the second derivative of the objective function or the Hessian matrix in the multidimensional case. Now the gradient vector of a function plays an important role in all these methods, and these methods are often classified as gradient based methods because they use some permutation of the gradient vector to come up with the search direction. Now these methods are fast and efficient in a local sense, and essentially in many problems where there are a large number of design variables. So by large, I'm talking of tens of thousands or a million design variables or so on. We find that the methods in this chapter are very useful, especially the conjugate gradient method. Now, much of the success of these methods depends on certain properties of the gradient vector, and we are going to look at some of these properties now. Now, the first property of the gradient vector is that the gradient vector c of a function f of x at some point xk is normal to the tangent plane. So essentially you can visualize a function f of x which is a curve in space, and you can think of a tangent at a particular point xk. So if you have a curve in simple one dimension, you have a tangent line. If you have it in space, then you have a tangent plane, and essentially at this particular point c dot t equals 0 is valid on the surface fx is equal to constant at the point xk. So this statement mathematically means that the gradient vector is normal to the tangent plane. Now we will prove this particular point now. Now consider a curve C on the surface. So this is a typical surface or the objective function. F x1, x2, x3 all the way to xn is equal to constant. Now let S be a parameter on this curve C. Then a tangent vector on C at point xk is obtained by differentiating each of these components with this S parameter, and again that we denote by this symbol bold capital T. Now we see that fx is constant here on the surface, and therefore the directional derivative of f is going to be 0. So df by ds is equal to 0, and so I can write df by ds using the chain rule as df by dx1 into dx1 by ds plus similar terms with x2, x3 and so on to all the way df by dxn into dxn by ds. Now if you look at this equation very carefully, you will see that this df by dx1, df by dx2, df by dxn are all components of the gradient vector, and the second series of terms which are the dx1 by ds to dxn by ds are all components of the tangent vector, and therefore this equation essentially can be written in a simple vector form as c dot t equals 0, which is essentially the fact that we are trying to state here is that the c vector and the t vector are normal. Now let's look at the second property of the gradient vector. So this property is that the gradient represents a direction of maximum increase for f of x at xk. Now to prove this, we are going to create a vector u, which is a unit vector that is not tangent to the surface, and t is some parameter in the direction of this particular vector. So the derivative of fx in the direction u at xk is defined as follows. So df by dt, going back to the basic definition of a derivative, would be fx plus epsilon u minus fx by epsilon in the limit where this epsilon tends to 0. So this is the derivative definition, and what we are going to do is we are going to find an expression of fx plus epsilon u using the Taylor series and then actually find this limit. So using the Taylor series expansion, fx plus epsilon u can be expanded out like this. So the first term is fx, then there are all these terms with epsilon here. So they are u1 df by dx1 plus u2 df by dx2 plus un df by dxn. So essentially the gradient vector into the u terms, and then further terms which are HOT terms. Now these ui are the component of the unit vector u, and the epsilon square terms are the HOT terms. So now I can subtract these two here and I can obtain the numerator part of the term we saw in the last slide, and so this is going to be this value here. And now this value, you can see that if you divide by epsilon and let epsilon tend to 0, only this part of this particular expression is going to remain, and the remaining parts are going to be decimated. So therefore df by dt would become simply this expression, which would become c dot u. Now this is a scalar product or a dot product, and therefore I can write it as df by dt is norm of c into norm of u into cos theta. And now I can look at this in a more physical manner. Now if you want to look at the maximum rate of increase of this function f of x, that would happen when theta would be 0, because that's when this would be maximum, because cos theta is 1. And so df by dt is a minimum and u is in the same direction as c. Now maximum rate of decrease of this function f of x would happen when theta is 180 degree, cos theta is -1, and there df by dt is a minimum and u is in the opposite direction to c. So these two particular concepts are very important. The first concept is what we set the theorem to be, and the second concept is what we use in optimization in terms of the search direction. So we come to a very important concept in optimization. At any design point xk, the gradient vector ck represents the maximum rate of increase of f of x, and therefore negative of ck represents the maximum rate of decrease of f of x. So that is the very important theorem in optimization, is that the negative of the gradient vector points you around the direction of maximum rate of decrease of f of x. Now the third property of the gradient vector is that the maximum rate of change of f of x at x is the magnitude of the gradient vector. So we'll prove this as follows. So again, going back to our previous mathematics, since u is a gradient vector, df by dt was norm of c into norm of u into cos theta. This we saw based on the definition of the scalar product or the dot product. Therefore, the maximum value of df by dt in an absolute sense would be simply the norm of c, because remember the cos theta maximum value is 1 and u is a unit vector, so there it's gone there. So again, the maximum value of this would be essentially this norm of C. So therefore, the maximum rate of change of f of x at x is the magnitude of the gradient vector. So we see very important properties of the gradient vector here. The first one lets you visualize your gradient with respect to the tangent plane. So essentially, if you are at any point on a curve, you make a tangent plane at that point, and the normal to this tangent plane is going to be the direction of the gradient vector. And if you reverse this direction of the gradient vector, that is take minus c of k, then that is going to point you to the direction of steepest descent or the direction of maximum decrease in the objective function. And in the next lecture, we are going to cover the particular method which uses d is minus c as the search direction, and that's the first and most simple method in optimization. And then we will see the pros and cons of this method, and then further look at ways to improve the gradient method by creating or using some aspects of the previous search directions and so on, which is the basic idea in the conjugate gradient method. So I'll stop this lecture in this point and I will see you in my next video. Thank you very much, and please subscribe to my channel for more such videos.